Hi, welcome to today's Science Talk. I'm delighted to be your host today. My name is Dr. Miriam Axel. For those of you who are joining us for the first time, usually smoother sailing. Appreciate your patience in this. Really glad to have you here. You can watch the full 2024 series as well as the 2025 series on demand on our website and our YouTube channel. That's unu.edu/INWEH/science-talks with an S at the end. Today's talk is reservoir dynamics in water-stressed regions. I'm really delighted to introduce our speaker today, Dr. Milad Aminzadeh, who's a senior scientist at the Institute of Geoinformatics at Hamburg University of Technology in Germany. He earned his PhD in environmental systems science from ETH Zurich in Switzerland, and his research integrates data-driven approaches and physical modeling to study environmental and hydrological processes, with a particular focus on evaporation and energy partitioning dynamics of terrestrial surfaces. Without further ado, I will pass it over to you, Milad. Thank you so much. And you're muted.
Can you hear me now?
Yes, we can.
And I have already shared my screen. Can you see my slides?
Yes,
make
we
it
can
full
see it.
screen as well? Yes.
Now it's full screen.
Perfect. So I can start, right?
Yes.
Great. Thank you. Thank you, Miriam, for the kind introduction. Hello, everyone. It's a pleasure to present one of the ongoing research projects in our institute, which is about the water reservoirs. Before I start, I should say this is a teamwork, and this is the result of a teamwork, and what I'm presenting it's just a summary of what we have done, our key findings, basically on behalf of our team. Okay. I'd like to start my talk with a few words about the importance of reservoirs. Water reservoirs have been at the core of supporting irrigation and livestock water demand since the dawn of civilization. They simply alleviate the impact of precipitation variability and seasonal water shortages, especially in dry regions of the world. This nice map, which is from Global Dam Watch, it shows us the global distribution of water reservoirs. In fact, human-made water reservoirs could be, I don't know, dams, impoundments, storages, river barriers, and so on. We have them almost everywhere, but perhaps with a higher density in China, India, in Europe, and across the United States. In this plot here, we see the increase in the number, surface area, and storage capacity of reservoirs since 1900. We see almost from 70 years ago, around 1950, we have a jump in water reservoirs. Relative to that time, today we have around 10 times more reservoirs. Of course, it's a relative percentage, the vertical axis, but it shows us the jump in number of reservoirs. Understanding the reason for this jump perhaps is not that difficult. If you look at the world population, almost around 1950, we see a massive increase also in the global population. At that time, around 1950, we were around 2.5 billion, and today we are around 8 billion. So we had to increase our storage capacity to provide water for our agricultural, industrial, and municipal activities. But I guess we all agree the main reason was food production for this rapidly growing population. According to Lehner et al., published in 2024, we have around 4.4 million human-made reservoirs, larger than 1,000 square meters. Altogether, they are providing a storage capacity of around 8,000 billion cubic meters of water. Think about this number. This is around 4% global lake storage volume. Because of these human-made reservoirs, we are increasing Earth's terrestrial surface water area by more than 360,000 square kilometers. So we are storing water, but because of the increased area, we are exposing it to more evaporative losses. This is very important, especially in dry regions with very high atmospheric evaporative demand. Our knowledge in hydrology and global water cycle already tells us that around 60% of all precipitation that occurs over terrestrial surfaces it returns to the atmosphere again in form of evapotranspiration. So someone might think about evaporation loss from these human-made reservoirs and the challenge of storage versus evaporative losses. So in our institute, we try to combine global remote sensing data and physically based modeling to address this paradox of water storage and evaporative losses in water reservoirs at different scales. The first part of the work that I present today is focused on small agricultural reservoirs. Here you see an example of actually small agricultural reservoirs in an agricultural area in Spain that simply provide water for irrigation purposes, especially in the absence of large-scale storage infrastructures like dams. They often need less resources for construction, management at farm scale, but there is a big issue around them. They are often ignored in the present inventories of surface water bodies. Of course, there are studies similar to the one I showed you earlier, but our knowledge about these reservoirs mostly relies on the statistical analysis, extrapolations, power law estimates, and so on. If we think somehow it makes sense because, for example, in comparison to the reservoir of a dam, detecting such small reservoirs is quite a challenge. So we try to identify the spatiotemporal distribution of these reservoirs and also quantify their evaporative losses. In the second part of the work, we focused on the role of human-made water reservoirs in intensifying regional and transboundary water conflicts. Here you see the satellite image from Chanime reservoirs. These are in the transboundary Helmand Basin. It's a basin shared between Iran and Afghanistan. Look at the scale. These are quite large reservoirs, and I'm not sure you can see on the satellite image around, you can see lots of agricultural lands. So these reservoirs are basically providing water for all those agricultural activities. So we can say without them, probably life wouldn't be possible in such dry region of the world. But we believe high evaporative losses from these reservoirs intensify water shortage problems and the transboundary conflicts between Iran and Afghanistan. We will see our analysis later. And the last part of the presentation, the last part of the work, looks into the dams as the iconic elements of human-made water reservoirs. I will show you later our analysis of evaporative losses from dam reservoirs. As I said, the first part of the talk is focused on small agricultural reservoirs in water-stressed regions. Here we have the map of MENA, Middle East and North Africa. Almost 2/3 of the countries in Middle East and North Africa are suffering from water-stress problems. We have marked croplands with the dots on the map. We have quite an extended agricultural area in MENA. And of course, these small agricultural reservoirs, you see, I have shown 3 of them in this inset. They are significantly contributing in sustaining agricultural activities in MENA. Such reservoirs, these small agricultural reservoirs, they might be fed from different sources, for example, from rain and collecting runoff water, from rivers and natural streams through agricultural canals, or even in some cases, we might use the precious groundwater to fill these agricultural reservoirs. When we look at the variation of precipitation in MENA, we see over the past 30 years, in many regions actually that are shown with red, we have a decline in the precipitation rate. At the same time here, we have also, actually we saw a drop down in the groundwater level. So from one side, we have less precipitation. From the other side, we have a drop down in the groundwater level. These are perhaps suggesting the abstraction of the precious groundwater to fill these reservoirs to support agriculture. But what's the contribution of these small agricultural reservoirs in local water management, in local water budgeting? What about their evaporative losses? To answer these questions, first we needed to detect the extent of these reservoirs. We used Sentinel-2 satellite images with 10-meter resolution to identify the spatiotemporal distribution of reservoirs in MENA. Sentinel-2 was first launched in 2015, and if I'm correct, June 2015, the first set of data was available from December. So we did our analysis from 2016 to 2023, a period of 8 years. We implemented several steps to get sure our water detection algorithm is accurate enough. For example, for a region, depending on the satellite overpass, per month, we might have 2-3 satellite images. Over a year, we can think about 30-40 satellite images. But we only used those images with less than 20% cloud cover to get sure what we are finding as a water body, as a water reservoir, is actually reliable. At the end, we applied the well-known normalized difference water index, which is based on green and near infrared bands, and we set a threshold value of 0.2 to identify water pixels. Here you see an example of identifying small agricultural reservoirs in an agricultural area using Sentinel images. When I say small agricultural reservoirs, I mean reservoirs smaller than 0.1 square kilometer or smaller than 100,000 square meter. Why this size? Because this is the size that's often ignored in the present databases. So what we know about them mostly comes from statistical analysis, extrapolations, and so on. Below in the image, below you see some of the reservoirs that are detected in that agricultural area. I really don't want to go through the details, but when we talk about an agricultural area, you can already think about perhaps the extent of rivers, I don't know, ephemeral streams, agricultural canals, or other water bodies. So we had to implement lots of masks, filters to get sure what we find as a water body, as a small agricultural reservoir is really reliable. Once we detected these reservoirs, next step is to estimate their depths and their volume. I guess we all agree that collecting information for the individual reservoirs at this scale is close to impossible, if not impossible. So we had to rely on the present power law estimates to quantify the volume of the reservoirs. We used the one that was proposed by Mahdi et al. You can see the relationship, the power law here. So once we have the 2D satellite image of the reservoir, we can use this equation to estimate the volume. Okay, now let's look at the results. We actually divided the agricultural area in Middle East and North Africa into pixels or grid cells, each one 50 times 50 square kilometer. And then within each pixel, first we identified individual reservoirs and we calculated the cumulative area. Here you see on the left-hand side, you see the cumulative area of reservoirs across MENA for the period of 2016 to 2023. What I'm showing here is just average values, but definitely we already calculated yearly values separately. On the right-hand side, you can see the storage capacity of these reservoirs. In total, we found more than 133,000 water reservoirs with a total area of 1,400 square kilometer. Our estimation shows the storage capacity, the total storage capacity of all these reservoirs is around 1,200 million cubic meter of water. We looked into the top 5 countries with the highest cumulative area of reservoirs. Turkey, Pakistan, Iran, Iraq, and Egypt are the top 5. Not a surprise because they already have lots of agricultural production and agricultural water withdrawal. So we thought it might be more accurate if we normalize cumulative area of reservoirs based on the cropland area for each country. This is the map you are seeing here. And according to this analysis, this new analysis, we found that the highest density of reservoirs, I'm talking about the cumulative area of reservoirs, relative to the cropland area is now seen in Bahrain, Emirates, Qatar, Western Sahara, and Kuwait. Okay, since we have detected the extent of reservoirs, I mean, we know their spatiotemporal distribution. So now perhaps we can quantify their contribution in the local water management. To do so, first, we need to estimate the agricultural water use per pixel. We use the available data sets of irrigation and livestock water consumption and provided this map for the agricultural water use within each pixel. Remember, in the previous slide, I showed you the cumulative storage capacity of all reservoirs within each pixel. Here we have agricultural water use per pixel. So the comparison between these two, probably it will give us a picture of the contribution of small agricultural reservoirs in local water management. Below, you see the ratio of the stored water to the agricultural water use within each pixel, for each pixel, actually. We see some pixels with this ratio more than 1, even some more than 10. That means they are storing more water than their agricultural water demand. But when we look carefully, we see quite lots of pixels. They have a value less than 0.01, or let's call it 1%. We need to be careful about this 1%. First of all, our estimation for the volume of the reservoirs is based on this very strong assumption that agricultural reservoirs are only filled once a year. But in reality, many of these reservoirs might be filled multiple times during a year. So the effective volume that they are offering could be much more than what we estimated. So we believe in some cases, what we are providing here, the numbers we are providing, is a kind of conservative estimate. The other point that we need to think about, that even if we believe this 1% contribution, we shouldn't forget that this is the 1% that fills the gap of water availability during dry spells. Imagine as a farmer when there is no other alternatives for water resources. This 1% actually provides water for irrigation, for livestock consumption. So it's actually a lifesaver, this 1% of water availability in many of the pixels that we are seeing on the map. Okay, next step was to estimate evaporative losses from reservoirs. We have different approaches for quantifying evaporation from a water body. Some, for example, they use satellite remote sensing, modest surface temperature as an example. So once they have the surface temperature from satellite, then they can quantify evaporative losses from a water body. There are some other approaches. They rely on locally calibrated parameters like Penman-Montis type approaches. But here we decided to solve the 1D energy balance equation. You can see the partial differential equation here. We decided to solve the 1D energy balance equation in depths of the water body to find the vertical water temperature profile. And more important than that, to find or to estimate to calculate, the surface temperature. So once we have the surface temperature, we can also calculate evaporative losses. In this model, of course, we looked into the energy exchanges of a water body with the atmosphere above. We had radiation, latent heat flux, sensible heat flux. At the bottom, we took into account the role of conduction, heat transfer, and of course, the interception of radiation at the bottom of a water body. Lots of details. I really don't want to talk about them. For example, think about the eddy thermal diffusivity, the impact of mixing, how wind might change temperature profiles, stratifications, and so on, radiation attenuation, and so on. I really don't want to talk about those details. In summary, once we have the meteorological variables for water reservoirs, if we have the boundary condition, I mean wind, radiation, air temperature, humidity, we can run the model and we can calculate evaporative losses for that reservoir. We first evaluated our model based on available evaporation data from a research reservoir in Iran. Here you see the comparison for a period of 1 year. It was between 2019 and 2020. Overall, model looks doing a good job. I think the total calculations for the annual evaporation based on the model was only 4% less than the measurement. And of course, we see the model nicely captures seasonal variations of the evaporation. On top now, you see the grid cell analysis of potential evaporative losses. How we calculated that? We assumed within each pixel, within each grid cell, we have a typical reservoir, and then considering the meteorological variables within that pixel, for example, air temperature, humidity, radiation, wind speed that we already extracted from the MERA2 datasets, we calculated potential evaporative losses from those agricultural reservoirs within that pixel. You see, we have our calculation actually shows some hotspots for evaporation in MENA, for example, in eastern parts of Iran, southeastern Iraq, and along the Nile River, we have quite high values of evaporation rate, even more than 3,000 millimeter per year. So before, within each pixel, we we calculated the cumulative area of reservoirs. Now here, we know what's the potential evaporation rate from reservoirs within each pixel. I mean, the volume of water that's lost by evaporation per square surface area. So if we multiply these two, cumulative area by the evaporation rate, we get the evaporative losses for each pixel individually. Our calculation shows in total from all small agricultural reservoirs in MENA, we have per year around 2,400 million cubic meter of water that's lost by evaporation. That's a big number, but we need to be careful. Our calculation it's for the entire year. So we run the model from January to December. But in reality, many of these reservoirs, they might be empty for certain periods. So what we are calculating is kind of upper bound for evaporative losses. Okay, so far, we know where is the location of these reservoirs, where they are located, how much is the evaporative loss from them. But now the question is, what's the fate of this evaporated water? With the help of our colleagues in Saudi Arabia and by analyzing global moisture trajectory datasets, we found that the majority of the water that evaporates from agricultural reservoirs, it's transported away via atmospheric circulation processes, and at the end, it precipitates somewhere else out of the MENA region. At basin scale, we might think, okay, within a basin, once water evaporates, if it returns again in form of precipitation, we may not consider that as a loss. But in this case, we already saw precipitation is decreasing. We have quite high agricultural demand, water demand. So most probably the precious groundwater, we are abstracting it, filling these reservoirs, but because of the inefficient storage, water is simply lost to the evaporation, and then with atmospheric circulation processes, it goes away and precipitates somewhere else. Our analysis showed that the main beneficiaries of the evaporated water from reservoirs in MENA are India, Iran, Turkey, Ethiopia, and Russia. Sorry. Small agricultural reservoirs and lack of information about them is not only an issue in Middle East and North Africa. Such information is also missing in other places, for example, in Europe. Perhaps you have heard in media about the conflicts over the extension of agricultural reservoirs in France. Because of the drought conditions, especially in the recent decades, farmers are trying to increase the number of reservoirs, simply increase their storage capacity. but environmentalists and locals are against them. And currently there are lots of conflicts and, of course, very strong controls on the construction of new reservoirs and their exploitation. So we extended our analysis and we looked into the small agricultural reservoirs in water-stressed regions of Europe. In particular, we focused on Italy, Spain, and Portugal with a very high level of food production. These three countries together, they have around 440,000 square kilometer agricultural area with a very high also water withdrawal. Together, the water withdrawal in the agricultural sector of these three countries is around 44 billion cubic meter of water. We had, in this case, a little bit different approach relative to what we did in MENA. In MENA, we directly used satellite images and extracted the information regarding the reservoirs. But here we used an already available dataset, global surface water GSW dataset, with a resolution of spatial resolution of 30 meters. This dataset provides information for the surface water bodies from 1984 to 2021. But we did our analysis just for a period of almost 2 decades, from 2000 to 2020. Similar to what we did in MENA, first within each pixel, for example, we identified reservoirs, and then we calculated the cumulative area and storage capacity. In total, in Spain, Portugal, and Italy, we found around 93 square kilometer water reservoirs smaller than 0.1 square kilometer. We also observed quite an increasing trend in the number of reservoirs. At the beginning of the study period in 2000, we had around 6,000 reservoirs with a total area of 46 square kilometer. But at the end, in 2020, everything was almost double. We had 12,000. We detected actually 12,000 reservoirs with a cumulative area of 93 square kilometer. On the right-hand side here, you see the results of our calculations for evaporative losses. We estimate from all agricultural reservoirs in these three countries per year, around 72 million cubic meter of water is lost via evaporation. It's around 40% of the storage capacity of all reservoirs. Someone may think that, okay, relative to that 44 billion that I showed you here, this 72 million cubic meter of water is really nothing. It's 3 orders of magnitude smaller than that number. But if we gauge it with the cost of desalinated water, which is often proposed as an alternative to provide fresh water for agriculture, the direct economic value of this evaporated water is around $140 million per year. Plus, we need to think about the environmental and ecological consequences of desalination. Okay, so far we have been focused on small agricultural reservoirs, how they contribute in local water management, how they support local irrigation. But there are cases that human-made reservoirs intensify transboundary conflicts. As an example, we looked into the case of the Helmand Basin. The basin is marked with red in the satellite image. It's a transboundary basin shared between Afghanistan, Pakistan, and Iran, but let's say mostly Afghanistan and Iran. During the past few decades, the basin has experienced frequent droughts. At the same time, the population is growing quite fast. So that means we need to provide more food for this rapidly growing population. Or let's make it a little bit more accurate. We need more water for agricultural production to provide food for this rapidly growing population under such water stress conditions. Under these conditions, two countries, these two countries, Iran and Afghanistan, they have tried to increase their storage capacity. And this has caused this has intensified already existing conflicts between them over water resources. You can see already in this news that's reflected in the media. Sorry, I forgot to say that in the Helmand Basin, Afghanistan is the upstream country, Iran is the downstream country. So the water goes from Afghanistan to Iran through the Helmand River, and at the end it goes to the Hamun wetlands. We have three main dams in Afghanistan: Kajaki, Arghandab, and Kamal Khan. But Kamal Khan, relative to these two, is not that big. These three together, they are offering around 3,000 million cubic meter of water storage capacity. On the Iran side, we have those human-made reservoirs, four reservoirs that are called Chahni reservoirs. And we believe evaporative losses from water reservoirs in the basin in such dry region of the world. Look at the satellite image. It decreases the storage efficiency of these reservoirs. In the absence of monitoring data, reliable estimates, this will intensify water shortage problems and the conflicts between Iran and Afghanistan over these water resources. So we used satellite remote sensing data to first identify the extent of these water bodies. Each year, we looked into the dynamic of the water storage within each water body. And then we calculated evaporative losses from them from 2001 to 2023. Here you see the results of our calculated evaporative losses from the main storage infrastructures. I mean, on the Afghanistan side, Arghandab and Kajaki. In Iran, the four Chahni reservoirs. On average, we see every year we have around 300 million cubic meter of water that's lost by evaporation from all these reservoirs. We have a jump in the in evaporative losses in 2020. If I'm correct, the calculated value was around 485 million cubic meter of water. That's a lot. Also, when we look at the bars, we see also a jump in evaporative losses since 2009. To be a little bit more accurate, a jump in evaporative losses from Chahni reservoirs. This is actually the year Chahni number 4, this one, which is actually the biggest one. It was filled for the first time. So area increased, and then you can imagine a very high rate of evaporative losses. So, as I said, when we look at these bars, it seems a majority of the evaporation that happens from the reservoirs in the basin, it's happening in the Chahni reservoirs. When we looked at the ratio of evaporation loss to the storage, we see this number for Chahni reservoirs is a number between 13 to 20. On average, let's say 16-17%. So 16-17% of the precious water that's stored in these reservoirs is simply lost via evaporation. Where does this water go? We used a similar approach as what we did in MENA, and we looked into the fate of evaporated water from all main storage infrastructures. I mean, Arghandab, Kajaki, and the four Chahni reservoirs. When we ran our calculations, the results were quite surprising. Only 8% of the evaporated water from these reservoirs returned to the basin in form of precipitation. The majority, 92%, somehow was transported away with atmospheric circulation processes, and then it precipitates somewhere else away from the basin. Let's review the situation. We have a basin under water stress condition. Two countries, Iran and Afghanistan, both are trying to store more water because the population in that region is growing. They need to produce more food. They need more water for their agriculture. But because of the inefficient storage, the majority of the water is lost by evaporation, and at the end, it precipitates somewhere else. Improving the water storage efficiency is not only a problem in the Helmand Basin. That was only one example. At global scale, we have quite high evaporative losses from dam reservoirs. To showcase that, we looked into the 10 largest dam reservoirs in water-stressed regions of the world. You can see the list of these 10 large dams, somehow some of their specifications and so on. We had, for example, Lake Nasser, Eufaula, Okeechobee, and so on. When I say lake, in fact, I'm referring to the reservoir of that dam. On the right-hand side, you see the results of our calculation for the annual evaporation rate from each of these reservoirs, from each of these dam reservoirs from 2000 to 2020. So for each of them, we first extracted the extent of the water body and then their meteorological data from MERA2 and then the calculations. We see in some of these reservoirs, they have quite high evaporative losses. For example, Lake Nasser, in some years we observed the evaporation rate could be more than 3,200 millimeter a year. That's quite a high rate of evaporation. We estimate the total evaporation from all these 10 large dam reservoirs in water-stressed regions could be around 26 billion cubic meter of water. So such framework that integrates satellite remote sensing, mechanistic modeling, it offers a quantitative tools that provide data, knowledge for informed decisions for the design and construction of new water storage infrastructures. Below, you see the results of our analysis to see how much water might be lost via evaporation from typical dams in basins across the world. As you see, we have some basins with very high rates of evaporation. In some of them, evaporation goes even more than 2,000 millimeter per year. What does it mean? Shouldn't we make any reservoir in those basins? Of course, this is not the message. The message is that we need to be careful about this often ignored impact of evaporative losses. We are providing some additional, let's say, information, some additional, if you can call it knowledge, that tells us we need to improve our water storage strategies. So we believe this kind of effort, this kind of analysis will contribute to several UN SDGs as well, especially those related to sustainable agriculture, food production, water security, and so on. At the end of the talk, I would like to thank my colleagues. Without them, definitely the work wasn't possible. The head of our institute, Professor Nima Shukri. Thank you, Nima, for all the insightful comments, supports. Our PhD students, Sankirs and Hannes, and of course, our former master student, Noemi. What I showed, the results that you saw, basically is the results of their work. Our international colleagues, Professor Calvin Madani from UNU-INWEH Canada, Professor Amira Alkuchak from UC Irvine, Professor Paolo Dodorico from UC Berkeley, Professor Ibrahim Hotayet and Dr. Matthew Zampiri from KAUST in Saudi Arabia. Actually, the atmospheric circulation modeling was done by Matthew. Thank you so much, and I will be happy to answer the questions if there is any. Thanks a lot.
Thank you so much for really, really fabulous talk.
Thanks.
My first question is, I mean, it's really quite staggering, the amount of evaporative losses, even from small reservoirs. How do you see your findings shaping the global conversation around reservoir management? Do you think that we need to rethink how we design and manage reservoirs?
Definitely. As I said also in the talk, in few places during the talk, I said that the numbers that we are calculating or estimations, they are definitely saying us that we need to improve our water storage strategies. We need to think about improving the storage efficiency. Probably in some regions, I understand about the economic considerations as well, but probably just making open water reservoirs in some places is not the first solution. We need to think about the possible losses. Yeah, definitely.
And in terms of data sharing, I mean, you mentioned having data from colleagues in Saudi Arabia. What are some of the possible challenges and maybe strategies for ensuring open access to data on water storage?
Well, actually, the calculation that was done by our colleagues, if I got the question correctly, in Saudi Arabia, they just did the atmospheric circulation modeling for us. We provided the extent of the reservoirs, their associated evaporative losses, and then we wanted to see where this water goes. And then, based on the available models that they had, they calculated for us, they simulated for us the fate of this evaporated water. But the most of the results that I presented, they are already published. Also, some of the results, they are still under review. But definitely, what we have found, they are publicly available if someone is interested.
We'll be sure to share that as well, and remind our colleagues and attendees online to please put your questions in the Q&A.
Hi, Milad. It was a very nice presentation. I think it put a lot of provocative questions that how to do, because you have one way you have to you need the water for irrigation and those purposes, and on the other hand there is no other alternative than groundwater. So what are the options there when we say that this reservoir is not optimal options?
Yeah, as I said, in some places, definitely we don't have that much losses from this open, let's call them open agricultural reservoirs. But we saw already some hotspots of evaporative losses. So in those places, maybe an open reservoir is not the first solution. So if we have resources available, maybe, I don't know, deepening a little bit reservoirs, because there is a definite, it's not a linear relationship. I know that, but definitely if we have deeper reservoirs, evaporative losses would be less. Or, for example, if there are ways to cover the reservoirs, take them even under the ground. These are possible scenarios, but of course, we need to also think about the resources for these kinds of alternatives, because making an open reservoir, probably in terms of the costs, efforts, that's the easiest option. But in certain places, this easiest option is not the best solution. We need to think to alternatives to somehow suppress this large evaporative losses.
Also, if I followed correctly, the reservoir water source is from groundwater. Is they extracted, or how? What is this in the MENA region that you said? The water is coming from the groundwater, extracted by manual extraction. How the reservoir getting the water?
Yeah, I need to say that this is basically our speculation based on the indirect evidence. We looked into of course, this wasn't the objective of the work. We were not looking into this question that where does the water come from? It was just our speculation based on this fact that we looked into the long-term precipitation patterns. We saw we have drop down. On the other hand, we saw a decline in the groundwater level. Groundwater is going down. And for most of these countries, agricultural production is being more and more. So in such region that you don't have that much alternatives. I mean, the river network, when you look at the global maps of the river networks, it's quite sparse in Middle East and North Africa. So you don't have that much options to fill these reservoirs. So our speculation for the discussion we had was that, okay, most probably, according to the evidence we are seeing, it's coming from the groundwater. But that would be a very, very interesting question to see what is the exact source of the water to fill these reservoirs.
Yeah, I think that could be another interesting question for research.
I agree, definitely.
And then if the groundwater is a source of water, then we could use deep tube well instead of putting reservoir for irrigating. So that could be an option. So
Exactly.
Yeah, thank you. So maybe you have a question in the Q&A.
Yeah, there's a question from Nika who says, have you calculated the amount of water loss due to evaporation and transpiration in high evaporation areas where groundwater storage is possible and compared it with surface water resource conditions?
Yeah, well, we didn't do any calculation regarding the transpiration. Whatever we did was just related to detected reservoirs. So we had surface water bodies, we detected them, we classified, and then we calculated direct evaporative losses from them. We didn't look into any transpiration. The second part of the question, I didn't get, sorry.
Was whether you looked at evaporation and transpiration in high evaporation areas with groundwater storage where it's possible and compared it with surface water resource conditions.
We didn't do that, but I can imagine that would be also very interesting to look in. But we didn't compare it with others surface water available surface water resources in a region. But I can imagine it's already interesting to have a look.
So I think to clarify, I think what he means is comparison the efficiency of groundwater storage versus surface water storage. So if you can recharge aquifer instead of, so if you can do aquifer recharge instead of putting water in the reservoir, with that, which one is more efficient? And I think in some parts of Iran, in Fars province and other places, we know that aquifer recharge is also a viable option. I think that's the question.
Thank you, Kawajan. That's correct, yes.
Is there another question?
Yeah. Well, thank you again.
I can ask questions. Yeah. I thought there wasn't.
No, this.
Okay. Yeah. So Milad, can please stop sharing your screen so we see you better. My picture is black and white. I feel I'm dead.
Sorry.
I was the only one there. So thank you for your wonderful work and research. And of course, it's I think we have to also clarify for everyone that this is not a recommendation, or we don't have the verdict that surface water reservoirs are bad, and so we have to leave them out of I would say the portfolio of solutions. Still, I think the world doesn't have a better solution in some instances, so they still remain as one of the options available, and indeed one of the effective options to regulate flows. But we know that they come with a lot of major ecosystem problems, environmental issues, social and economic issues, so that over the years we have learned a lot. Not only that, we don't even know how to deal with the old ones and get rid of them when they are not as efficient as they were when we designed them and constructed them. But it's certainly like, your research opens our eyes and I think adds a dimension that we've maybe talked about it in passing, but we didn't have real methods for measurement, especially at this large scale. And one other question, so I think, one good question that came was, in some places, can we compare this against other options? And you mentioned in some places there is no option. So of course we need to consider those other options. There's also the option of alternative designs, right? So the size of the reservoir, the depth of the reservoir, and all of those can, so with your type of calculation, we can now add that dimension. That would be extremely helpful. And if that becomes part of the mass balance so essentially calculation, so people know the effective storage of reservoirs, and that's very helpful. And then another question, because of your comparison of what was happening in, for example, Southern Europe versus MENA, the question for me is or maybe even it's more of a common now. So can we compare the option of small reservoirs against big reservoirs? And in this case, I want to ask if you have an answer for this question still. Is it better to have one big reservoir instead of many small reservoirs? Do we have an answer to that question yet?
In terms of calculations, no, we didn't calculate, but I can already assume, based on what I have learned during the past few years working on this topic, and from our knowledge in fluid mechanics, I don't know, atmospheric, land-atmosphere interaction and so on. Definitely, when you have a big reservoir with the, let's call it same area as multiple small reservoirs, in that case, of course, the impact of lateral heat transfer, the impact of boundary layers over the reservoir, these are really important parameters that would affect evaporation from each of these small reservoirs. So my understanding is that, although, as I said, we didn't have any calculation, but my understanding is that if we have a big reservoir instead of multiple small ones, that big reservoir would be more efficient in water storage in comparison to multiple small ones that are distributed around somehow, I hope.
That's a very, of course, and we have to highlight the caveat that it also depends on the climatic conditions and many other factors. People should know that. But that's a very interesting one, because in terms of water storage efficiency, a bigger reservoir is best, or better maybe. But then in terms of the environmental impacts and socioeconomic impacts, it's certainly a worse option. So then again, balancing that is an issue. And the other thing is when it comes to regulation. So if you have a fair regulator, having a centralized system can be better than having each farmer having his or her reservoir. So that's another issue that comes with the institutional design and operations. So lots of food for thought, and highlighting the fact that evaporation is a loss, but sometimes it's a bigger loss than what you think, because it's not contributing to local precipitation, and that's something that at least has not been a big concern, or has not been part of the big debates. So knowing that how the big reservoirs around the world are impacting climatic and weather conditions in areas remote from them is something, and it's indeed a strategic loss, or loss of assets for countries that have to be taken into account. Or some countries might be benefiting actually from the environmental loss damages in other countries because of the dams that have been built. It's good to take those into account. Again, I always learn new things from you, and thank you for that, for the great work you and your colleagues are doing at the Technical University of Hamburg, or Hamburg University of Technology. For those who don't know, we have a hub at UNU has a hub at the Hamburg University of Technology that is focused on engineering to face climate change, finding solutions to effectively cope with climate change when it comes to mitigation and adaptation. And Dr. Milad Aminzadeh and his colleagues have been very, very productive and have been doing very interesting research. So thank you, Milad. Please pass our regards to your colleagues, and thank you everyone who've been watching us. Back to you, Miriam.
Thank you again so much.
Many thanks.
Really wonderful presentation. We look forward to welcoming you and your colleagues here to UNU-INWEH, and we look forward to seeing you again next week. Next week we have a session with Professor Grace Oluwasanya. Thank you again, and we'll see you soon.
Thanks a lot. It was a pleasure. Many thanks.
Thank you.
Thank you.
Thank you so much. Bye.